students, in this class I am going to explain about the differentiator topic. In yesterday's class I already explained about an ideal differentiator. In this class I am going to explain about the practical differentiator. In this practical differentiator we have the circuit like this. We have the R1 and the Vi and the node B and the node A taken to the op-amp, and the R component is resistor, and the RF and the CF are the feedback resistors and the feedback capacitance to the inverting and the output terminal of op-amp. So here I am going to explain the derivation part for this practical op-amp. Here I am going to apply nodal analysis at node B. Apply nodal analysis at node B. We can get I is equals to I1 plus I2. Here we have a current I1. Current flowing through this R1 resistor is I, and the current flowing through this RF resistor is I1, and the current flowing through this capacitance is the C2. So here apply node analysis at node B, and we have I is equals to I1, entering current is equals to leaving current at the node B. I is equals to I1 plus I2. So here I can write I is equals to I1 plus I2. So we have already know that I is equals to V by R. So if from this I is equals to V by R means I is equals to Vi of S by R1 plus 1 by SC1. 1 by SC1 means transconductance of capacitance. Transconductance of capacitance is written as 1 by SC1. So I is equals to V by R. In the place of an I is equals to V by R, Vi of S by R1 plus SC1. So here that is equals to I1. In place of an I can write I1 is equals to V1 by R1. So here V1 is V0. Minus V0 means in the non-inverting terminal we are having the minus term here. Minus V0 of S by RF. RF is a resistor across this I1, and minus V0 of S by 1 by SCF is a transconductance of capacitance is written as 1 by SCF. So here I can substitute my I2 term here, V0 of S by 1 by SC1. Transconduct of capacitance is written as 1 by SCF. So here I want only the terms which are having only the terms output V0 of S is equals to V0 terms. I want finally V0 by V1. V0 of S by V1 of S. So for that I can take a V0 of S to this right side. V0 of S terms in this right side. V0 of S of 1 by R1 plus SCF. 1 by SCF is taken to input, taken to numerator. So 1 by RF plus SCF is equals to taken this input term to this side minus Vi of S into SCF by 1 plus SCF into R1. So here V0 term is taken to this side and the V1 term is taken to this side. For the getting of an V0 by Va, V0 by Va is equals to minus, we can get minus SC1 RF by 1 plus SR1 C1 of 1 plus SRF C. So here we can get the V0 by Va term from this minus C1 RF by 1 plus SR1 C1 of 1 plus SRF C1. So here, if you put in the place of an RF or CF as R1 C1, in the place of an R1 C1, if we can put RF CF. So V0 of S by V1 of S is equals to minus SC1 RF by minus SC1 RF by 1 plus, in the place of an RF CF we can put an R1 C1, then we can get 1 plus S R1 C1 whole square. This is the first equation. So we can get the terms like this. The term like this 1 plus SC1 R1 plus in the place of an R1 C1 we can put RF CF here. So here R1 C1 we can get. So we have the next equation as taken like this. If here RF C1 is greater than C1, here RF C1 is greater than R1 C1 or RF C1 but RF C1 is less than T1, then equation 1 becomes, in the equation 1 is here V naught by V by of C minus SC1 RF by 1 plus. So here RF R1 is less than R1 C1. So here we can eliminate the numerator. In the place of a numerator we can ignore this denominator. We can ignore the denominator. Then we can get in the place of an V naught by Vs is equals to V naught by Vs is equals to minus S into RF C1 V1 of S. So here we can get the denominator term. Why? Because RF is greater than R1 C1. So in the final equation we can get like this: V naught of t is equals to minus RF C1 into d by dt into V of t. So this is a practical differentiator term. So here I am going to explain about the frequency response of practical differentiator. We have the final equation V naught by S Vi of S is equals to minus S C1 RF by 1 plus S R1 C1 square. So here R1 C1 is equals to RF CF. So in the place of a frequency response, I am going to derive the frequency response of practical differentiator. So in the place of an S, we are going to put the J omega. J omega means J 2 pi F. You already know about these terms. V naught by J omega is equals to minus, in the place of S, minus J omega C1 RF by 1 plus J omega R1 C1 whole square. So here omega means 2 pi F RF C1 by 1 plus J 2 pi F R1 C1 whole square. So FA we can consider in the place of an FA as 1 by 2 pi RF C1. In the place of an FA we can assume 1 by 2 pi RF C1. In the place of an FB we can put 1 by 2 pi R1 C1. So here now in the place of an 1 by 2 pi F R1 C1 is 1 by F by FA. In the place of an 1 by 2 pi RF C1 is F by FB. So here the magnitude term for this equation becomes as magnitude is given as A is equals to V naught of J omega by Vi of J omega is equals to magnitude of minus J of F by FA by 1 plus J F by FB whole square. Then the magnitude becomes like this: A is equals to F by FA. We already know A plus IB. Magnitude term is the square root of A square plus B square. So from this square root of 1 plus F by FB whole square, F by FB by 1 plus F by FB getting cancelled here. The gain in dB is 20 log F by FA by 1 plus FB by FA. So here when we apply this, when F is greater than FB, then gain will be decreases. That means the gain will be decreases. When F is greater than FB. When F is greater than FB, the gain will be decreases. When F is less than FB, that means F is less than FB, the gain will be increases to the plus 20 dB per decade. When F is greater than FB, then frequency will be decreases. So this is about the frequency response of a practical differentiator. So advantages of using a practical differentiator is at higher frequencies the gain will be limited. So circuit is very stable. At higher frequencies also the gain is limited. That means gain will be less. Gain will be limited. That means gain will be not high and not will be low, but it is at the middle state. So it is limited. So circuit is stable. Or in the ideal differentiator, the circuit is unstable due to the presence of high frequencies in that circuit. So due to R1 C1 and RF CF, the combination of higher frequencies noise is just reduced. Due to the combination of R1 C1 and RF CF, in the ideal differentiator we are taken only R1 C1, but in the practical differentiator we are going to take the R1 C1 and the RF CF. So by the combination of R1 C1 and the RF CF in the practical differentiator, noise will be reduced. This is about the practical differentiator. Next topic is a difference amplifier. Next topic is difference amplifier. It is another topic in the third unit. It is a difference amplifier means subtraction of our two input voltages is possible with the help of op-amp. A subtraction of our two input voltages. That means here we have added two input voltages, inverting and non-inverting terminal on the output. So subtraction of these two, I1 minus V2, we are getting the difference amplifier. Circuit called as subtractor is also the circuit. This circuit is called as a subtractor or difference amplifier circuit. So here we have the difference amplifier circuit. Here we have V1 and V2 are the inputs, and the I1, I2 are the current flowing along the circuit, and the node A and the node B are taken here. RF is a feedback resistor connected to the non-inverting terminal, and also RF is a feedback resistor connected as the inverting and the output. I1 is the current flowing through this circuit. I2 and the I1 are the current flowing through along this circuit. So here V1 we have a difference amplifier means V0 is equals to V01 plus V02. So here where V01 is the output voltage of the circuit when V1 is present and V2 is grounded. When here we are going to take the output, V output is equals to V01 plus V02. When we are considering V01 is the output of the circuit. V01 is the output of circuit. When V01 is the output of circuit, when V1 is present, and V2 is grounded, then V02 is output when V1 is grounded, when V2 is present. So here when V01 is taken when V1 is present and the V2 is grounded, and when V02 is output when V1 is grounded and V2 is taken, V2 is present. So it is the logic of using this difference amplifier circuit. So here we have the differential. There are two cases in the difference amplifier. Here we have two cases when V1 is present and V2 is grounded. Two cases. That means V1 is having the source and V2 is taken as 0. So here the circuit looks like an inverting amplifier. When V1 is present, that means when V1 is present, the circuit looks like an inverting terminal. When V2 is grounded, the circuit looks like an inverting terminal. So here the equation for the inverting terminal is taken as in the V01 is equals to minus RF by R1 into V1. You already know about the inverting terminal of op-amp of the circuit. The equation is when the inverting terminal of op-amp is connected across the op-amp, so V01 is equals to minus RF by R1 into V1. V0 output, the V1 is inverting terminal, V output is equals to minus RF by R1 into V1. When this is the case 1. In another case, we have a non-inverting terminal of op-amp. When V2 is present and the V1 is grounded, it is acts as like a non-inverting terminal of op-amp. So here, when V2 is present, when V1 is absent, then it is a non-inverting terminal of op-amp. You already know the from the second unit, we have a derivation for the non-inverting mode of operation in the closed loop operation. So V2 is equals to 1 plus RF by R1 into VB. VB means that means voltage across node B is VB. So V2 is equals to VB. So here V0 is equals to 1 plus RF by R1 into VB. Apply voltage division rule. Apply voltage division rule here. We can get here apply voltage division rule. here apply voltage division rule. We can get VB is equals to V2 into RF by R1 plus RF. Voltage from the voltage division rule, VB is equals to V2 into RF by R1 plus RF. From the voltage division rule, V2 into RF, the components across the voltage is RF, and the total number of components present in the circuit. Some of the components present in the circuit are the R1 plus RF, and the voltage across the component is RF into voltage across the terminal. So here we can get an output like this. V02 is equals to V2 means V02 is equals to V02 is VB into 1 plus RF by R1. In the place of an VB, we can put this equation. VB is V2 RF by R1 plus RF, RF plus R1 by R1. Then V02 gets like this, V2 RF by R1. When RF term cancelled, when V2 RF by R1. This is the equation. When V2 is present and the V1 is 0, that means it is a non-inverting terminal of op-amp of the circuit. The equation is V02 is equals to V2 RF by R1. Then V1 is we are getting 1 plus RF by V1 is getting minus RF by R1 into V1. So V0 will minus RF by R1 VI in the case of an non-inverting terminal. In the case of a non-inverting terminal, we are getting V0 is equals to V2 RF by R1. So this is about the total. We have the total output V0 is equals to V01 plus V02. V01 is minus RF by R1 minus RF by R1 into V1 and the V2 RF by R1. From that we can get an total output RF by R1 into V2 minus V1. Total output is RF by R1 into V1 minus V2. You already know about the difference amplifier from the closed loop operation like this. RF by R1. We remember in the second unit the closed loop operation of modes of operations in the difference amplifier. The final equation is this. The final equation also is this. So from the difference amplifier, from the differential mode of operation, the equation becomes like this: RF by R1 of V2 minus V1. So difference amplifier means differential amplifier means we are having the differential amplifier logically V2 minus V1. That voltage difference between two input voltages V2 minus V1. So finally we have an RF by R1 with V2 minus V1. When RF is equals to R1, when these two terms becomes equal, then the equation becomes V0 is equals to V2 minus V1. That once it is a subtractor. When RF is greater than R1, when RF is greater than R1, we can get V0 is equals to RF by R1 of V2 minus V1. So it is called as a difference amplifier. Difference amplifier. This is about then a difference amplifier topic. Very easy. This is related to second unit closed loop operation, closed mode of operation. You can go through that video and also you can get an information about this difference amplifier. So here I am going to explain another topic, V2I converter, voltage to current converter. Here voltage to current converter, the output load current is proportional to the input voltage current. So here voltage to current converter. Voltage to current converter means the voltage to current converter, the output load voltage, the output load current. Current I is proportional to voltage across the input. I output is equals to proportional to input voltage. The output here, the output current in the is the input current. VA converter converts the when VA converter is used. Here the VA converter is there. That means voltage to current converter. That means output final current voltage is converted to current. Voltage is converted to current. So current is proportional to voltage, input voltage, proportional. That means what is the voltage applied here? And the same current, same type of current is converted to the output. So voltage to current converter here we are using. So here There are two voltage to current converters. One is voltage to current converter with a floating load, and another one is voltage to current converter with grounded load. So here we have first is a floating load. Voltage to current converter with floating load. Here, if floating load means we just added the load to the network. So we have and simply inverting terminal and the non-inverting terminal. In this inverting terminal, we are applying the R1 resistor, and the non-inverting terminal is given to source, and the IL is the current load at the load at the floating load, current at the floating load, and the AB is the node, VD is the difference between two input voltages. So here I is equals to IL is written as VI by R1, VI by R1, VI by R1. So we have I is equals to V by R now. I means IL, load across the final output load is equals to voltage across this non-inverting terminal VI, and the resistor across the inverting terminal is R1. So final equation IL is equals to VI by R1. VI by R1. So here this load current is proportional to input. Load current is proportional to input voltage, and the circuit works as a voltage. Works as a voltage to current converter. Voltage to convert. We are converting the voltage to current by using this circuit. By using this floating load circuit. Here output load is proportional to load is a current load. Load current here, input load current, input voltage, load current is proportional to output voltage, input voltage. Here load current, output load current is proportional to input voltage. Here ZL is the output load and the input current is VI. So ZL is the ZL means IL. So IL is proportional to VI. IL is proportional to VI. So finally we derive the equation IL is proportional to VI. That means load current. What is the current? The load IL. IL is proportional to input voltage. So finally we are going to derive the voltage to current converter with floating load. The equation is finally IL is proportional to VI. So here voltage to current converter with a grounded load. So here this is the network of voltage to current converter with a grounded load. So here the input op-amp is given to the resistor R, and the resistor R here I1 is the current flowing through this non-inverting terminal. IB is equals to 0 and IB is equals to 0. R and the R the current connectors across this non-inverting terminal, and the output voltage, and the load R is connected here. Load R resistor is connected here. For this non-inverting terminal we are going to apply the ZL load ZL, that means the grounded. It is a grounded load. With the grounded load we are taken here the grounded load. Load is connected to ground, so it is called as a loaded ground. Load is connected to ground, so it load here. This is ZL is a load here. The current flowing through this load is IL, and it is a grounded, so it is called as a grounded load here. Simple circuit. For this circuit we are adding the load here, grounded load. So here we are having a VD is taken as 0 from this circuit. VD is 0 and the VA is equals to VB. That means the voltage across B is equals to voltage across A. So VB is equals to VA when VB minus VA is also taken as 0. Why? Because the differential voltage is taken as 0 from the circuit. Apply nodal analysis at node A. Apply nodal analysis at node A. We have a nodal analysis. The entering current is I1. The entering current is I1 plus I2 plus the entering current. At node A, the I2 is the entering current and the I1 is the entering current. is equals to IL is the leaving load is the leaving current. Load IL is the current. Load current is the leaving current. So we can write from the circuit. From the I1 is the current at the node A, and the I2 is the current at node A, and the IL is the leaving current. So we can write I1 plus I2 is equals to IL. So IL. So we are going to derive the load current here. Finally, we want IL is proportional to VI. So output current is proportional to input voltage. So IL is equals to I1. In the I1, I is equals to V by R now. I is equals to V by R. So V means voltage applied across here is VA. Voltage across VA. VA is the applied voltage here. VA minus VA by resistance across this is R plus V0 means V0 here. V0 minus VA by R. Simply VA by R. V0 minus VA by R. Applying the V is equals to I is equals to V by R now. So V is VA minus VA by R and V0 minus VA by R. So we can get IL. R is taken to this side. IL R is equals to VA plus V0 minus 2VA. VA plus V0 minus 2VA. So we want VA term these two side, this side. So VA is equals to VA plus V0 minus ILR by 2. So this is the first equation. VA term as VA plus V0 minus ILR by 2. So this is the first equation. So we have for the inverting amplifier. For the inverting amplifier, we have the equation. From the inverting amplifier, we will have the equation V0 is equals to 1 plus RF by R1 into VA. From the inverting amplifier, we have for inverting amplifier we have V0 is equals to 1 plus RF by R1 into VA. From this equation, this is a standard equation from the inverting terminal. So inverting terminal, we have an inverting terminal here. Inverting terminal is taken as V0 is equals to 1 plus RF by R1 into VA. V output is equals to, for the inverting terminal, V output is equals to 1 plus RF by R1 into VA. So here we have the standard formula from the inverting terminal as 1 plus RF by R1 into VA. So 1 plus RF means we are taken here from the circuit R. From the circuit RF means we are putting R here. So simply we can put in the place of an RF R into VA. So we can get simply 2 VA. R plus R plus R by R into VA. So we can get an 2R by R into VA. R gets cancelled, then we can get an 2 VA here. So V0 is equals to 2 VA we can get. So substitute the value of VA in equation 1. In the equation 1 we have an VA now. So in the place of an VA we are going to put VA is equals to V0 by 2. For the simplification purpose, VA is equals to, we can put V0 by 2. So in the place of an VA, put V0 by 2 is equals to minus VA by 2 minus IL into R by 2 plus V0 by 2 plus V0 by 2. V0 by 2 gets cancelled. Then ILR by 2 is equals to VI by 2. We can get ILR by 2 is equals to VI by 2. Then load current IL is equals to 2 gets cancelled here. IL is equals to VI by R. So we can get an IL term as a VI by R. Where R is constant, we can write IL is proportional to VI. IL is proportional to VI. Finally, we can get equation IL is proportional to VI. So this is about the current with grounded load. Finally we can get IL is proportional to VI. So this is the equation from the voltage to current converter. So here I have another concept, current to voltage converter. Simply this is very simple. This is a very simple topic. Current to voltage converter. The current to voltage converter, the output voltage is proportional to the input current. Here in this current to voltage converter, here we have simply output voltage. V output is proportional to input current. In the voltage to current converter, we derive IL is proportional to V in. In this current to voltage converter, we are going to derive the output voltage. Voltage output is proportional to input current. Okay. So here we have V output is proportional to input current. So here we have a circuit which is converting the current to voltage converter. Voltage here, the current to voltage converter, the output voltage is proportional to input current. The output voltage is proportional to the input current. That means V output is proportional to the I. We have the circuit for this. We have the circuit for this. We are going to derive the current to voltage converter. Very simple way. So here we have an IS is the source across this inverting terminal, and the node A is the non-inverting terminal. Non-inverting terminal is kept at ground. IS is the current flowing through this R. That means a feedback resistor. V0 is the output here. Then here we have the circuit analysis. VD is taken as 0. Simply we are always taken VD is taken as 0, and VA is equals to VB. That means VB minus VA is equals to 0 from the VD differential voltage. Since VA is equals to 0, VB is equals to 0. Now VB. Now we have I is equals to V by R. I is equals to V by R. From this we have an IS term here. IS is equals to V means V voltage across this terminal is VB minus VB. Voltage across this node B is V. VB minus V0. V0 is here. V0 grounded voltage means we are taking V0 by RF. V0 here. VB minus V0 by RF. VB minus V0 by RF. Here RF. IS is equals to VB minus V0 by RF. That means IS, the voltage current applied to this is finally we want IS is proportional to V. Sorry, not this. V in is proportional to IS. That's it now. V output is proportional to IS. So here VB minus voltage apply rule will be nodal analysis here. VB minus V0 by RF by VB minus V0 by RF. Then IS here. Sorry, here IS, in this IS is equals to nodal analysis here. VB voltage across this is VB minus V0 by here RF by RF. Then we can get in the terms of an IS, VB is 0. So IS is equals to VB as taken as 0 minus V0 by RF minus V0 by RF. So V0 is equals to IS into RF minus IF into RF. Finally, we are having the constant RF. RF is constant here. RF is constant here. So V0 is proportional to IS. V0 is proportional to IS. So output voltage is in the voltage to current to voltage converter. Output voltage is proportional to input current. Input current is IS. and the output voltage is V0. Input current is Is and output voltage is V0. So input current is output voltage is proportional to input current. This is about an voltage to current converter. So these are the topics in this third unit: voltage to current converter, difference amplifier, and the current to voltage converter, and the practical differentiator. So here, and next class I am going to explain about another topic, which is an various circuits of an differential amplifiers. So here, this is about the topics of the voltage to current converter, current to voltage converter. Thank you.